Okay, so we'll continue with this discussion of containers on ARCHER2. And I should have said up front actually that if you're wanting to get deeper into containers with a bit more specific detail, then there is a whole ARCHER2 course on containers, which has been given in the past, by one of my colleagues, Andy Turner. And I will just look out the web page for that, where you can go through the course materials in more depth. I'll put that into the chat. And that goes, there's a whole day on effectively doing Docker containers at the beginning, and then a whole day on using and configuring and setting up Singularity containers. So much more detail than I go to in this lecture. But if that's something that's useful for you, then it's available in the past repositories and the materials online, which is good. So as I was saying, we have containers, we can use them. We can use them in a number of different ways, even if we don't need to load a module to do it, like I was doing, but Singularity is installed by default, both on the compute nodes and on the login nodes. And as I said, we have a number of pre-built images, or there are Docker images you can pull down, or there are pre-built images online you can use. The nice thing about Singularity is it is configured for this sort of user interface on high-performance computing systems. It's designed in this multi-user environment so that when you first load it up, it knows who you are. So the container is not necessarily being built on ARCHER2. It's maybe been built elsewhere, and it's been built by somebody using a root user or a different user. But actually, here's an example here. If I actually load up the container, I can then go into it, and it knows who I am. So we can see in these slides here, and I can do another demonstration at some point. But when I do a shell into this container, this hello world container, which you yourself can try and play around with in a practical session. And I ask it who I am. It says Adrian J, and it says what groups I'm in, and you can see I'm in group Z0, Z19, and Archer, TDS, and all sorts of different groups there. And these are coming directly from the ARCHER2 system, from the host system, and that enables the container itself to interface correctly with the file systems and the permissions we have on a host system. Now, it doesn't wholesale import all the groups, so it won't know about other users on the system. But it knows about me, and it knows about my groups, and that means it can work out which files I'm allowed to access and which files permissions I have. Now I can see in this command here, I'm using a special -b command here, and I've not covered this yet. But basically, when you load up Singularity, a Singularity container here on the login nodes, there's a certain amount of a file system which comes in with you, but no more. And now is probably a good time for me to demonstrate that. So let me share my screen again and do some more dangerous live coding. Let's have a look. Here we go. So I'm here now, and I can demonstrate that it knows who I am. So this is on the plain login node. You can see the nice thing is that this shell text changes, so I know where I am. So I say, who am I here? And I say groups here. And if I go into the container, which if you remember is loading up effectively a brand new operating system with only me inside it. If I look who's there, there's nobody in the system. If I say, who am I? I'm still Adrian J. And if I say my groups, it's pulled those in quite nicely. And you can see actually I'm in my home file system here, and it has all my files from the whole file system. So even though these files weren't created inside this operating system, the Singularity runtime, when it started up a container, has pulled in that home directory. It's what we call mounted or bound the home directory, so I can access my files there. But actually, if I look in here, it doesn't have anything else, right? So it doesn't have anything else apart from a plain sort of what you would see with a standard standard Linux system. You can see there's no work file system in here for me to go and have a look at, and there's no other things in here. So if I look in the opt directory, there's nothing there. Whereas if I go into this system here, I can see that if I look in my opt directory, it has all sorts of stuff installed in there. This is where the Cray libraries installed, and the compilers installed, and R's installed, and all sorts of things are installed there. And if I look at my main directory, my login nodes, you'll see there's home and home 1, 2, 3, 4. There's work, and that's where my work directory is. And this is because by default, Singularity only pulls in your home directory and nothing else. So all of the file systems are missing from this operating system. But I can bring more file systems in if I want to. And I'll get the order of this wrong because the order of this does matter. I can bring more file systems if I want to by using a -b command and telling it the file system I want to bring in. So in this case, I want to bring in my work file system. And now if I inside here, I can now go into my container, and actually I can go into my work file system now because I've brought that in, and all my work things are there. You can see my R install from my work directory is there. And if I want to be really fancy, I can rename it, so I don't have to keep it as work/Z19 Z19. I could just call it, work dir. And now if I look here, there's no work there anymore, but there is a work dir. And if I look at it, that just has all my files in it from work. So Singularity doesn't by default bring in lots of file systems, but it lets me bring in file systems as and when I need them to bring in data or environments that I need. Let me go back to my slides. Now you can imagine that's going to be important because I need my work directory when I run on the back end, so I need to bring that in. I also need to probably bring in all those Cray directories with pre-installed MPI libraries and compilers and stuff if I want to do anything sensible on this system. Now, there was a question earlier: can we use Singularity on the back end? Can we use Singularity through batch systems, etc., etc.? And the answer is yes, we can do that. There's a number of different ways we can use Singularity as this. So if we were just wanting to run Singularity as a normal program inside a single compute node, then I can just put it inside my batch script. So this is a normal batch script. It's saying I want to run one thing, 8 CPUs per task. I've given it 8 threads for the application, and then I just do Singularity run and the name of my application, and it will pick up the environment. It will run inside a single compute node. And so if I have lots of data science workflows where I've got lots of individual programs I want to run to process data, like we saw we could do before with running multiple jobs inside a single batch script, or doing Slurm array jobs, and then I can do exactly the same. I just need to, instead of doing S run in there, I just need to do Singularity run instead, and that will do what I want to. If I want to get a bit more complicated and run MPI applications inside your Singularity, which you may not want to do as a data scientist, it depends exactly what software you're running, then you need a little bit more care, and then you need a particular image, a particular container or container image, which contains an MPI library which is compatible with the one we're running on ARCHER. And really that means sort of MPI compatibility between hosts and container. And so this is an example batch script of doing this kind of thing, of running a container which has MPI in it to run an MPI application. And again, if you're not familiar with what MPI is, it's the sort of standard parallel library we use for writing large-scale applications on high-performance computers. It lets you send messages between workers on different compute nodes. And so this, if you want to use 5,000 nodes on Archer, you need something that can generally can send messages between those nodes. And you can see, for us, again, we've got a standard batch script here. I'm now running on 2 nodes. But there's a bit more stuff that's come in here, unfortunately, now. So to get Singularity to work properly on ARCHER2, where we can pick up the right MPI libraries and the right network libraries and stuff like that, we have to actually add in a bit more detail. And so we've got to add in this special environment variable called Singularity environment library path, LD library path, where we add in the Cray MPI libraries and then everything we need for them to work, and the little bits and pieces. And then we also have to add in any directories we need, and that includes the ones which contain all the libraries which my application will have been built with. And if we have all that, then we can just use srun and launch Singularity, multiple copies of Singularity, with a container which has got MPI inside it, and then that will run effectively. Now, again, there's more examples of this on the Archer website, and this actually we have these pre-built MPI images which you can play around with and have a look at, and we'll maybe do some of that in a practical session. But there's also, you may also want to use Singularity to compile applications as well. So if I take, for instance, this is one of the Singularity images we provide, mpitchbase.sif. So this is a container with the compilers in it to build your own MPI applications. And this could be a base for a container if you wanted to create your own containers on your own Singularity containers for ARCHER2 that you could take away, modify, add some software into it, and then import back into ARCHER2. But here I'm doing a compilation where I'm saying I'm running Singularity, but I'm calling the compiler from inside this image to actually compile an application for me. And so instead of using the compilers we have on the login nodes that are provided by Cray, we're actually using a compiler from inside this image, our own special compiler. And that could be, you need a different version of a particular compiler because your code doesn't work with GCC 10.2 or whatever it is. You need GCC 7.3. You could build a container with your own version of the compiler, but still interface with the MPI libraries on ARCHER2 and use that to move forward. It's then also, so that's how you can compile. This is how you can submit a batch job to run. You can also do an interactive run, so not a compilation, but an interactive run where we run that same thing we've built over here. So I've built my program here on the login nodes using a container, and then we do an interactive run where we start our job and run that job using the same container, but the executable lives in my work directory. It lives outside the container. It's just something I've compiled to the container, and I just pass it on and say, please run this for me, and away it goes to do that. So containers here give you that potential to wrap up some software in a container which you can then run without having to install all the extra software on ARCHER2, or it gives you a possibility to wrap up a development environment with a set of compilers and libraries inside it, which you can use to build your own applications on ARCHER2 without having to install them all there on ARCHER2. There are actually different ways of running parallel applications, large-scale parallel applications with Singularity using this MPI. And it gets into a bit more complexity there. So the one we were looking at here was called host mode, where we use the host MPI to run Singularity, and it requires this integration between the container to have a sort of compatible version of MPI installed inside it compared to the MPI outside it. You can also do it in something called bind mode, where you provide a container. It doesn't have any MPI in it, but you just bind in the MPI from the external, from the host environment, and let it interface up to that instead. So both of these work. If again, I don't think this is really the mode where most data scientists will be using containers, but if it is, then there's definitely more detail on the ARCHER2 container course or through the Aptainer manuals or online documentation about this kind of stuff. It looks a little bit hairy. It's not as hairy as it looks, as long as you follow the scripts that we have predefined. Okay, so there's a question in here from Jing. Can OpenMPI in a SIF be run on Cray machines like ARCHER2? Yeah, absolutely. It could. In fact, you can run OpenMPI on ARCHER2 without a container if you want. So the nice thing about ARCHER2 is that we have Cray MPI, so the Cray MPitch thing, but actually the network is the hardware and software configured in such a way which you can build your own MPI libraries if you really need them and install them. So for instance, you can build OpenMPI yourself on ARCHER2 and just run directly against that. Or if you wanted to use a SIF file, like a container file with OpenMPI in it, you could build a host version of OpenMPI and a container with OpenMPI and run that, and that both of those will work. So there's a little bit of benefit in some cases for using the Cray specific version of MPI, but you can get other versions of MPI running efficiently if you know what you're doing. I would say in the first instance, try and use the Cray MPI. In the second instance, if you need your own, if you say my application can't work with MPitch, it has to have OpenMPI, that's fine. But probably come to talk to us to make sure that you've compiled and configured your own version of MPI in an efficient way, so it's using the right networks, because it's quite easy to build MPI, the MPI library incorrectly, and it will work, but it'll just give you poor performance, and we'd like to avoid that if we can. But yes, you can use OpenMPI in a SIF on ARCHER2. If you are wanting to build your own container with its own MPI inside it, so we can do something like this host version here. Now, as I say, we can provide you a container with MPI inside it, so you don't have to build a new container. But a lot of times you will want to build your own containers. Then the way you do this in Singularity generally is there's two ways of doing it actually. The sort of gold standard way of doing it is to provide Singularity with a build definition, which is this file here, this stuff here, which says, you know, what image do I want to start with, what version of that image do I want to start, you know, what files am I going to pull in from the outside, and then set up the environment and build all the software we need when you're building the container, and configure the run script and those kind of things. So this is where you can start to customize your containers, where you could put in all sorts of software installs and inside this. And then with that kind of definition, all you have to do is Singularity build. You pass in this definition here, which is what this file up here is, and it produces you a container called whatever you call it here. Now, of course, the challenge is that I mentioned you can't do this kind of build on ARCHER2 because you don't have the permissions to run as a root user. So you'd need to do this on your own system, either on a system you have root with, or in a system where you've got Docker installed, because there is a mechanism for installing Singularity from inside a Docker image, and that's definitely possible as well. We've got documentation on that, but if those are the kind of things you need to do, that's what we need to do. It is also possible to actually take an image, and if you have the permissions, if you're in a system where you have root privilege, open it up in root mode, add software into it, and then squash it back down into a container and build a container that way as well. It's a little bit more complicated. It needs some extensions so that you can pack and unpack the container, but you can build containers like that as well in Singularity. So yeah, we're not really covering building your own containers here because we don't have a system available that lets you do it, and you need to have root permissions on your system and install Singularity locally to be able to build container images, or to have Docker installed on your system, and you can use a Docker Singularity container, which is always, I find, a little bit strange. So you're starting a container inside a container to build another container, but it's definitely possible. And as we pointed out before, all you need to do is create a definition file, and this is a much simpler one than we saw before, and then build it. Or if you're running it on a Docker system, build it like this, and then you get an image out the end of it. And you can make your container definitions much more complicated from that. There's quite a lot of documentation out there on making containers customizable and usable in the ways you need to. And we actually use some containers on ARCHER2 for things that are quite hard to install on the login nodes, but people want to use little programs and things like that. So containers are definitely a sensible option if you've got a tricky workflow, tricky program to port. They're definitely a good place to have a look at packaging up things and pulling them in, or if you've got a pre-existing sort of Docker container or something like that. And if you're going to use them in anger between groups of lots of collaborators and things like that, then it's worth looking into some of the extended functionality for things like signing containers for distribution and attributing them and things like that. Okay, so there's detail there. There's quite a lot of detail there. Again, some of it it's likely you'll never need to use. Some of it you may need to use, but it's here for reference for you. If you get onto Archer, you start trying to install something, it doesn't work. Where do you go? What are the things you need to do? One of the ways you can go is through containers. And then the other ways, of course, are installing your own Python or R modules or libraries. We just need to make sure we do that in a sensible way so they're available on the ARCHER2 system in the right place you need to run on the compute nodes. And so installing R and Python libraries is generally straightforward, but making sure they're on the compute nodes and on the work file system, well, they're available on the compute nodes from the work file system is sensible. And you may often have to tweak the compilers you're using for some of the packages to build. Always remember we have quite a lot of software already available on ARCHER2, so that's useful anyway. And then more complex software installs may benefit from containers. It needs a little bit of work. So basic container functionality is simple, but it needs a bit of work to get parallel file systems and parallel message libraries working properly. And as we've been saying as we go through the day-to-day, the key is making sure that our software is as efficient as possible. So part of that is what we've seen already, placement and binding for threads and processes. So just as we want to be careful when we're running normal programs on the compute nodes, we want to do exactly the same thing if we're running container programs to make sure that our processes and threads are in the right places using the hardware as efficiently as possible. And if we're building our own software or installing our own software, we want to make sure we're picking up those optimized maths libraries like Cray, Lipsci, that we're using the latest compilers possible and optimization options for those compilers to make sure our programs are as fast as possible. So one of the challenges, of course, with containers is that one of the reasons people use containers quite heavily is that they've got software which is difficult to build, or ends up being fixed on one version of the compiler because later versions of the compiler breaks the code. And of course, that's a bit of a challenge from our perspective in keeping codes as efficient and optimized as possible, because the newer the compiler, the more scope there is generally to have fast runtimes and fast applications. So there is a bit of a tension there between using containers to support software which is fixed on older versions of libraries and things like that. It would be a shame to see compute resources usage wasted because a container has been brought on, but it's using, it's not using optimized maths libraries, or it's not using, an optimized FFT library, or it's using the wrong message passing library, and so it's going over sockets and stuff. So even whilst using containers to support complex builds, it's sensible to keep an eye a little bit on that optimization piece and that making sure we're running programs as efficiently as possible. Yeah, and when you're porting your containers across, is there any place where you can upgrade part of them to use the latest compilers on ARCHER2 or anything like that? May be beneficial to you. Okay, so that's the end of the sort of container compilation porting lecture. Of course, there's a lot of devil in the detail here. So when you come to actually port the programs you want to port, if you are wanting to bring software onto ARCHER2, then you'll probably find that I haven't covered some bits or pieces which are probably more important or trip you up. And that's where people like me and Chris and William, who are on the call on this training session, are useful, because we have this whole support infrastructure which lets people helps people with these kind of problems. So if you do run into things like that, it'd be interesting to know. And if you have got a data science workflow which you'd like to start porting across to Archer now to test it out, now is a good time to do it, to see if this throws up anything of interest which we can fix now and then tell other people about. If there's any questions, let me know now, or let me know. Otherwise, what we'll do is there's a couple more practicals beyond the first one, which was to look at, so I've updated this first practical a little bit. If you reload the PDF, you'll see there's a little bit more in that first practical now. Let me just share my screen again. I'll share my tab. So I wanted you all to be up and running with placement stuff first, to check that that was working before we got onto anything a little bit more complex. So at the same time, there's also a little exercise where we can have a look at memory bandwidth performance. Now, again, you probably don't really care about raw performance characteristics of ARCHER2, but memory bandwidth is a good substitute for application performance for a lot of different applications. It's, a large number of our applications are really performance limited by about how much data you can move in and out of the processor, and so memory bandwidth benchmark is a good way of seeing, are you getting good performance or not on ARCHER2. So we've got a little program called Streams, which is one of these standard test cases for benchmarking memory bandwidth. And you can compile that, unpack it, compile it, and then run it and see what bandwidth you get for the different benchmarks. And then again, try playing around with the placement and binding to see, are there scenarios where you get better or worse performance? Are there scenarios that you want to avoid where you're getting quite low memory bandwidth performance because you're not spreading out across the cores or the threads? And you can have a little bit of play around with that. And then once you're done with that, there is a second practical in the same vein, which is the same thing, but looking at the I/O performance and looking at different striping parameters of I/O performance to see whether the striping of files across the Lustre file system gives you any benefit or not. And once you're done that, I'll put up a little practical for installing software and trying out the containers, and you can see how you're getting on with that. Any questions? If not, give the practicals a shot, and when you run into problems, let us know, and we'll give you a hand. And then what we'll do, let me have a look at my timetable. What we'll do is we'll come back at 2:45, so in 15 minutes, and we'll start talking parallel Python and Dask. But in the meantime, if you run into any problems, let me know, and I'll stick that third practical up so you can play around with. It's just going to be install some Python software yourself, install some R software yourself, and here's how you play with containers. Have an experiment and see how you get on. Well, it looks like some of you are getting on with the file system benchmarking, which is good. Just so that we don't entirely derail my schedule, what I want to do is get started on my next lecture. And don't worry, we've got time to come back to practicals. But let me start on my next lecture just so we're getting going. So we're now moving on from software installs and build and stuff to Python, and common ways we can exploit Python stuff here. Yeah, give me a second. I can say. Gene, which interactive S-run of Singularity is that? Is that for running an MPI program? Let me just share those slides again, actually, just to check which one exactly you mean. So this one here, this top one, InteractiveCompile, or let me just check my chat again. Page 16, or the bottom one or the top one on page 16. Let me copy and paste that here anyway for you. You would have to modify this command because this has my directories in it, so you'd have to change the Z19, Z19, Adrian J to whatever your project is, TA055, TA055, and etc. But let me just, and it also assumes that you've already compiled this hello world example here. So I'm running a specific example here, which is my own source code. If you need that source code, let me know. But that one should run. Now I'll say famous last words. It ran okay for me yesterday, but then I thought I was using a Singularity module yesterday. So, but let me just give it a quick check to see if it actually runs for me today. I'll be with you in a second, everybody. Just checking this one here. Yeah, that's working okay for me, but I'll check that I haven't got anything special set up in my environment and get back to you on that one, Jing. If it's not working for you, it could be that I've already set something underneath which lets that run okay for me. Okay, anyway, we can come back to it in the coffee break, but let me go on to the next one, which is Python. Okay, so again, we're not trying to teach you Python here. We're assuming that if you're using Python for your data science work, you already know Python. But it may be that you're at the stage where you know Python fine, but you haven't really tried to make Python workflows, Python programs go faster, because you've just got to a point where you're thinking about using something like ARCHER2 because your data sizes have got too big for you to run locally, or because you need more memory than's available and these kind of things. So what are your options? Now, as I say, we're not really teaching you Python here, but there are sort of two main ways we can think about parallelism. And really, I probably should have given this talk at the beginning of the day, but there's sort of two ways or at least I think about parallelism. And these are sort of map onto single node parallelism, or what I'll call shared memory parallelism. And that's using all the cores inside a single node. And then distributed memory parallelism, and that's using multiple nodes together. And this thing I keep going on about MPI, if you're not familiar with it, well, MPI is one mechanism for doing this distributed memory parallelism. So that lets you use multiple nodes together. Of course, MPI, the way it works, you can also use all the cores inside a node, but in a distributed memory fashion, you run lots of individual workers. They're all separate. There's nothing shared between them, and they just talk to each other over a network. That network might be inside a node, and that network might be outside a node, but they don't really care. Shared memory parallelism is you run one main worker inside a node, and it creates a bunch of its own little workers, threads, which can all share data backwards and forwards because they're all contained inside the main worker. They're all in the main worker's memory space. So you can use all the resource inside a node for one main task, but with lots of individual workers collaborating on that. Now, I know that's a very woolly definition of parallelism, but that's how it makes sense to me. Python itself doesn't really do, well, it does do parallelism, but it doesn't do sort of high performance parallelism. And there's a couple of reasons for that. Now, Python has what we call threading built into it. Threading being this way of having one main worker that can create its own mini workers to go off and do things. And that's what Python can do through the threading library. And this looks very much like if you'd ever done any programming in C with threads. You take a function in Python, and then you can sort of wrap it up into a little worker and start that worker off, and then you can finish the worker. And there's lots of complexities you can add in there, but really it lets you parcel up functions into individual workers and get them running. And it looks a bit like this. You define a function, use a threading library, and then you create threads and you start them, and then you can join them at a later date and wait for them to finish or automatically finish them. And if you were running this in C++, this kind of threading, then you could do parallelism there. You could get all those threads working at once. But unfortunately, Python, the way it works, it's interpreted language, actually doesn't let you run those threads at once. So it lets you create lots of workers, but only run any one worker at any one time. And that's through this thing called the global interpreter lock of a GIL, which means you can create a bunch of different workers, but you can't run them concurrently. You have to run them serially. So threading in Python in this mechanism is useful for some things, like asynchronous events, waiting for file access, which is going to happen in the future, keep creating workers for those kind of things. But it's not necessarily very useful for improving the performance of an application, by using more computational resources. Python does also give you a multiprocessor way of doing this. It's okay, William, we'll come back to that. I definitely want you to get you working on this. I'm surprised the capacity is so low, but I will check exactly what's going on here. 1 to 8 working is good, but I'll check what that is. It's useful to know as well, thank you. Python does also give you another mechanism for doing this, called multiprocessing. So this lets you create, instead of threads from a single worker, it lets you create multiple workers. It's more heavyweight, costs a bit more to do, but this doesn't have the same global interpreter lock. So you can create individual workers and they can go off and do their own work. And this looks very like the threading, but you can do sort of pools of workers and those kind of things. And as I say, this does let you do parallel work, but it's not really designed for high performance closely coupled parallelization. So when you've got to send data backwards and forwards, you can use queues and pipes, and you can yes, it's quite similar to Java multi-threading style things. So this definitely works, but actually if you benchmark it and look at how this performs compared to the other things we could do to do parallelism, it's not particularly quick, this kind of Python multiprocessing. And at some level, it's also stuck with inside a single node. So you're effectively having to do the work of writing some message passing programming like we do in MPI, but you're not really getting to use more than a single node. So this kind of parallelism is available in Python, but it's really designed more for distributed computing or for concurrent computing than it is for parallel computing, which I know sounds a strange thing to say because you could assume distributed and concurrent computing are the same as parallel computing. But what I really mean here is parallel computing as in quite tightly coupled, a lot of communication going backwards and forwards, a high amount of time spent processing data or doing calculations. So you're more than welcome to do those kind of parallelizations in Python, but they're not generally going to give you high performance. There are other ways to get parallelism in Python, and if you were on the Python course we did last week, you'll have seen some of these. Some of the libraries you can call from Python, NumPy and SciPy particularly, will call down to lower level libraries like Cray libsci, which do some parallelism themselves, do some of this shared memory parallelism to increase the performance of something like a matrix operation or these kind of things, matrix vector operation, these kind of large computational things. They'll call down to a underlying math library, which itself will go parallel. And you can do that yourself. So you can do native interface into C or Fortran or C++ code from Python. And as long as that underlying C and Fortran code is parallel, then you can get some parallelism out of that. So that is possible. And there are libraries which will also let you write direct MPI programming in Python. So again, we talked last week, part of this on the MPI on the Python course last week, MPI for Pi, where you can write your own programs which send data backwards and forwards between different workers. And so you can do explicit MPI parallelization like you would do in C and Fortran. And I know I keep going on about Fortran, but it is quite heavily used still on ARCHER2. Probably a little bit anachronistic to a data science workflow, but it is still underpinning quite a lot of the code we're running on ARCHER2. And so that's all there. But it's probably not the place people go when they're native Python writers and they want to go straight up to parallelism. Actually, there are other libraries that we can use to do this kind of functionality. And the one that we're going to have a look at today is Dask. So again, I apologize if anybody was on the course we taught last week. We looked at Dask again last week, so You'll have a little bit of overlap here, but we went through it pretty quickly, so you'll probably have forgotten it all, and it will be useful to reacquaint yourself to what we were talking about with the Dask stuff last week. So I appreciate we are, yeah, okay. We'll go to about half. We'll go to 3:30, take a break till 4, and then come back, finish this, and then do our lecture after that. And there's, time to do the practicals in your own, as you have time to do that. Okay, so what is Dask? Dask is a library, it's a Python library, and it's parts of it are pre-installed in that Cray Python module that we were talking about earlier. And it's a Python library with two main components. It has sort of what we call user interfaces on the left-hand side, what they call collections, which let you different ways of programming Dask, of interfacing your program to Dask. And then on the right-hand side, it has task graphs and task schedulers to take lots of different things and run them for you. Now, you can see on ARCHER2, we already have a scheduler called Slurm, and that takes programs, large programs, and runs them on the compute nodes for us. And then, so this here, the Dask scheduler, takes small tasks and runs those small tasks on compute resources that are available to them, including through Slurm if you want it to do that. Now, it may sound like an interesting approach, but it's not necessarily a particularly new approach in high-performance computing. People have been building task-based programming languages and libraries and systems for a while. The idea behind them is that it abstracts away some of the complexities of doing parallel programming from the user and gives you parallelism without you having to explicitly write, for instance, all the messages sending backwards and forwards that we have to do for an MPI program, for an explicit MPI program. So you can just define bits of work to do and then let the system decide how it does those and where it runs them and those kind of things. So as I say, there's lots of task and programming languages around, even in high performance computing. One that came out of US for single node work recently was, well, recent I say, it's probably 5 years old, 10 years old now, COCOS from the US, which is a C++ one for scheduling tasks inside a single node. Barcelona Supercomputing Center have for long been developing one called OMPSS, which is like a large-scale parallel one. And Dask is similar to these in a number of ways, except that it's designed and written in Python to provide you this high performance. Now, we don't tend to use task languages that much in computational simulation because there's a bit of overhead associated with your scheduler has to be as efficient as possible, otherwise you lose a little bit of performance. But on the flip side, they're much easier to program and much easier to write, convert existing serial program into something that's parallel without you having to do very much work. So there's very much a efficiency versus performance argument here, and Dask is, highly regarded for functionality it provides and the ease of programming, while still giving good performance. So what does it actually look like? Well, you give it functions, things to do, as I said. Then it decides how to split those up into work, or you may help it do that. And then it runs that work for you. Okay, and so this is an example of a Dask task graph where it's got a bunch of functions, inc. These are all the same function, and then double functions as well, and they've got outputs, and then all the outputs of those are combined into another function called sum, which produces a third, a final output for you. And you can see, well, maybe what this is trying to show you, I think, is that each one of these things here is independent, could be run in parallel or in serial if you want, but they're independent. But all of these need to be run before there's some functions run. And then once all those results are available, you can run some and produce a result. But you as a user don't have to worry about that. you can just say, I want to do some of these things and some of those things, and please go and do it for me. Now, the nice thing, of course, about Dask is that it has good interfaces for data science style languages or functionality. Particularly, it has 3 front-end built-in types. One called array, which maps to NumPy arrays. So these are sort of reasonably low-level data structures, but give you good performance for doing, lots of mathematical operations. The second one is data frames. So this maps directly to Panda data frames, and this looks like a 2D array, but also, is designed really to give you functionality which you could get from a 2D spreadsheet style thing, and is heavily used for data analysis. And then they have a third data type called a bag, which is designed for a bit more unstructured multi-type style data, which wouldn't really fit in easily into a data frame or an array, because it has different kinds of data within it, because it has irregular structure and these kind of things. And what Dask gives you is lets you build these structures and then distribute them across a set of compute resources, and then get the results back from them in different ways. You can, if you are so inclined, also build your own task graphs with Dask without having to use these underlying functions. So you can sort of directly build a task graph to say, well, okay, I'm going to write my own functions that do different bits of work, and then I'm going to try to run these functions together, and I don't have to use a Dask data frame or a Dask array or a Dask bag. I've just got a set of Python code that I want to parallelize, I want to run as tasks. Let me add those kind of things in, and away we go. And there's 2 different flavors of that. There's one called delayed and one called futures. Futures is a bit newer. Delayed was the original stuff. They do similar things, except delayed, effectively, you tell Dask about your whole task graph and then you get it to compute it, whereas futures lets you start computing things and then construct the task graph as things are going on whilst computations are happening. And then there's a bunch of supporting functionality that lets you do these things. Data movement, so moving data between workers, gathering and scattering. So collecting the data from different operations, or passing data out to be worked on before the operation starts, and some low-level synchronization functionality if you really need it, queues and variables and locks and those kind of things. That's all very abstract. What does it look like in reality? Well, if we go through the collections themselves, one by one, Dask array, which, if you remember, maps directly to NumPy arrays underneath, looks like this. So you import dask.array, and then there's a whole set of different ways of creating them, which mirror the NumPy libraries methods for creating these things. Here's an example of creating a random array using the Dask random module with a random function. I'm creating a 10,000 by 10,000 array, and I specify I want to split it up into chunks of 1,000 by 1,000. So this bit here at the end is what would be different than if you're just doing normal NumPy, adding the chunks in. You have to tell Dask, here's some data, this is how you split it up across the workers. And this is specifically true for the Dask array functionality. The other stuff, Dask bag and Dask data frame, you can get Dask to automatically partition the data for you. But here for the Dask array, you are manually having to tell Dask what to do. And there can be a little bit of complexity there in ensuring you get the right performance here or there. This is pretty simple. There's actually many ways to create arrays. So if you have a look at the Dask documentation, you can do binomial and normal, Poisson and random distributions. You can just create a Dask array directly from a NumPy array. So you create a NumPy array and then you just call a function which takes that and splits it up into chunks and ultimately will distribute it across workers. This approach is slightly limiting in the sense that one of the nice features about Dask is it lets you do out-of-memory computations. Out-of-memory computations would be considering, working on data sets or data structures which you could never load the full amount into your available memory in your compute nodes. But Dask, because it splits data up into chunks, will just read a chunk at a time and let you process all that. Now, of course, if you create a NumPy array, NumPy doesn't let you do that out of memory stuff by default. So you're sort of restricting yourself to things you can fit into data types. But you can make Dask arrays from NumPy arrays if these NumPy arrays are sort of more complex than you could generate with a normal functionality. And you can also create Dask arrays from files, particularly NumPy binary files and Z-array files. There's functionality to do that. Now, there's a couple of things that I've not mentioned here. One thing to mention is that the way that Dask works, it actually compiles down to the underlying functionality. So a Dask array can contain many chunks, and each one of those individual chunks is probably an individual NumPy array. That's a good question, William. So what we haven't talked about here is actual number of workers. So at this point in time, Dask is not making a decision about how many workers it's going to use. You've told it how many chunks you want to split up. And at some level, you probably want more chunks than you have workers. But this is not really doing anything about actual scheduling or numbers of threads or numbers of processes or anything like that at this point. There is functionality to specify how many workers you want. We'll come and see that. And specify, there's different functionality to use threads or processes or submit to the batch system. By default, for Dask arrays, you would get threads, and you get as many threads as there are cores on the system, on the node you're using. So like on an ARCHER2 node, that would split this up over 128 workers, or you get 128 workers here. Now you can play with that and you can change those values, but that's what it does by default. So the Dask array compiles down to NumPy arrays for the individual chunks, but it deals with the distributing of those chunks over workers. And the other thing to realize is that Dask for this stuff is lazy in the sense that it doesn't do any compute until you tell it to. So here I've done, import this, and this, but actually I haven't created any data at this point. I've just told Dask that I'm going to create some data. So let me see if I can give you an example of this. We will get there 1 second. My ARCHER2 terminal has decided to die at an opportune moment. Module load create Python. So again, I'm going to do some risky business in the sense that I'm going to try and do some live coding of things that I've not tried out just yet today. But let's see how this goes. So what I want to try doing is create that Dask array that we have in the slides there. Yeah, and so this is just using normal create Python. I've not done anything special here. I've not told it about workers or batch systems. If I print out what X is at this point, you'll see that X is not actually it's not giving me any data. It's just saying X is a Dask array. It's got a shape, it's got a data type, it's got a chunk size, it's got a chunk type, and you can see the chunk type is, the underlying chunks are actually NumPy ND arrays, but that's it. Not telling me anything else. I can't do anything unless I do a x.compute, and then that will force it to actually go off and say, okay, take this data, take it up into chunks, generate those chunks, bring the data back at the end, and it will go off and do that. So that's what I mean about it being lazy. By default, for a lot of the stuff that Dask does, not everything, but a lot, it tries to, it wants to construct as much of the task graph as possible before evaluating it. So until you call a compute function like that, it's not going to actually do anything in terms of developing or processing the data. And actually, this can catch you out, or it certainly could catch me out, when you're testing these things to try and benchmark and stuff. If you forget to put a compute in, then the program runs really, really quickly because it doesn't actually do any work at all. It just goes, oh yeah, I've created a task graph. Okay, I've finished now. But it doesn't actually produce the results at the end. So that's chugging away there. We'll come back to that. I'll come back to the slides. So that's what I mean by lazy there, as in you need to press you need to specify a compute to finish that off. And then there's a bunch of functions that then, or operations that Dask supports. Very, a lot of the NumPy functionality, but not all of it. So it will let you do on Dask arrays, arithmetic and scalar mathematics, reductions, so sums, means, standard deviations, tensor contractions, dot products, transposers, reorderings, slicing, and slicing across various axes, or using lists to pull the data out. And some of the linear algebra functionalities, SVD, least squares, sum solves, will let you do. And of course, these are all parallelized across the workers you have, depending on how you've split your chunk sizes up. Not everything's there. So much of the linear algebra functionality from NumPy isn't yet implemented. And there's a whole bunch of things which are not fully supported. So you can't do arrays of unknown shapes for everything. You can't do sorts, all kinds of sorts, and into lists. And some of the iterators, you wouldn't want to necessarily iterate across some of these functions, because what that will do is iterate each worker individually rather than across all the workers. So you have to think a little bit about the operations you do with a chunked array like this, because it is chunked across workers, and you want to make sure all the workers are doing stuff at once if you can. So that's Dask array. Data frame is the version which does which is the same as pandas data frames. Or it gives you the same functionality as a panda data frame. So again, you can say you import dask.dataframe, and then, for instance, you can read in a CSV file, pull in that CSV file. And by default, what it will do generally, the data frame, is it will give you one chunk per file, right? So Dask is great at reading in multiple files. If you read in multiple files, then you get a separate data frame, pandas data frame per file, and that's how it will split up across the workers. It is, of course, possible to actually split up a data frame across, to read in the data frame in different blocks sizes. So you can, there's a thing here called block size, and this is in megabytes, I think, or bytes. And you can specify what block size to read in a data frame, and that sort of does similar functionality to creating the data frame in chunks that are distributed off workers. So you can specify it, but you're not forced to in the same way that the Dask array forces you to specify a chunk size. And then there's a whole array of different ways to create data frames from CVS, from HDF, from JSON, from databases, from Dask arrays, and from bags and those kind of things. Once you've got a data frame created, you can then perform a lot of the operations that Panda data frame would give you as well. So independent operations on elements, on rows, find locations, aggregate across various things, do date, time, and those kind of operations. There's a bunch of group by, count and indexing their operations you can do, and some more involved functions like correlations, resampling, and those kind of things. You can also create, do group operations that require data ordering, so joins, sets, and group by applies. But it won't necessarily do everything that you could do in a Panda data frame, because again, you've got to remember that you split some of your data frame up across workers, and so that restricts what you can do, either in terms of performance or in terms of functionality. So the data frame, if you set a new index from an unsorted column, it will be expensive. Many operations that require that, things like group by or join on unsorted columns, will also be expensive. And there's a whole bunch of things that are not supported if you look through the API stuff. Operations that would always been slow in pandas anyway probably will still be slow in the Dask data frame. So iterating through by row and those kind of things. And again, this is because, you know, if you're restricting the amount of parallelism you can put in there by iterating individual rows without doing it in a way that's split up across the chunks, then or the blocks, then that will be slow. Right. Next is Dask bag, and then we can go into a little bit more detail in Dask. But that's half past, and I don't want to inflict my voice on you for too long. So we'll take a break here. We'll come back at 4. I appreciate we're overrunning a bit where I would like to be, so I'm not giving you as much time on the exercises as we would like. So apologies for that. But as I say, the exercises will be there for you to do in your time after this course, so you can always come back and have a look at them. And what would be useful is to get through all the lecture material before the end of the day. So let's take a break, come back at 4, and we'll do this, and then we'll go into R. And if you have any questions, let me know. Okay, apologies for the delay. So we have just been looking at the different Dask collections or in sort of programming interfaces to simple data structures that Dask will provide you with. The final one is Dask bag, which is a bit more general, a bit less focused on existing functionality. So effectively, it will take something like a list or a set from standard Python functionality, and it will turn it into something which is parallelized across workers. Now, it allows unordered collection of data with repeats in it, and the data can be of different types, just like a list or a set could be in Python. And it lets you distribute that across your workers. There is a caveat that the set is immutable, like a tuple would be in Python. So once you've created it, you can't change it. You can do operations on it, you can create new bags from it and new sets from it, but you can't actually change that existing set. Now, of course, it's probably evident to you all that you could create a bag from a simpler data structure, like something where all the data is exactly the same, and you could store it in a Dask array. And that's absolutely true. These can be interchangeable, interoperable data wrappers or data constructs, but the bag tends to be slower and less functional, have less things you can do on it. So it should really only be used in the cases where you genuinely have sort of unordered and different typed data altogether that you want to process through. So there's a bunch of data operations that the Dask bag enables you to do. So filtering, group by, folding, mapping. You can see it's really designed to do sort of initial data processing, data cleaning kind of work to pull out the things you want from this, but not do massive amounts of more complex processing on top of that. So parallelizing simple computation on unstructured or semi-structured data, taking in text files, log files, or user-defined Python objects and extracting data out of them, but you can then push into the rest of a Dask framework to do sensible work with. Now, there's a bit of complexity here. So I said earlier that by default, what Dask will parallelize across is threads and give you as many workers as you have on the compute node you're running on. That's not true for bags. So the reason that Dask can use threads for arrays and data frames is actually it's calling down to NumPy arrays, or it's calling down to Panda data frames underneath to hold its actual data, and the actual workers, the threading, is going on at that level. And that avoids this global interpreter lock problem we have, because we're not doing parallelization in Python. Dask is doing parallelization in Python. It's doing parallelization in the lower level functionality. It's doing parallelization in the underlying library it's using. A bag, on the other hand, is designed to interface into standard Python code, so standard Python lists and sets and sequences. And so if it wants to do any parallelization there, it can't use threads, because if it did, it would be stuck with this global interpreter lock and it wouldn't get any parallelization there. So what the Dask implementation of bag actually does is it uses processes, that multiprocessing that we saw before, to do the parallelization. So if you're using bags, when it's not going to use threads by default, it's going to use processes by default. It'll still try and use as many processes as you have cores available, but it's doing something slightly different and potentially something slightly less efficient than the threading, which is one of the reasons why we want to avoid bags if we can use anything else. Of course, if this is the only data structure you can use, then it's better than not parallelizing on this data structure. And we can create bags from text and from sequences like lists, Python lists, from URLs, from ranges, and a bunch of other kind of things. And then we have operations we can perform on these bags, like accumulate, and which is like a reduction operation. We can add things up, we can accumulate all these kind of operations. Actually, I'll see if I can demonstrate a couple of these. Again, with some very unwise live coding. Let me check if my window is still open. I think it is. So let me share this window. It would be nice if Collaborate let you share two screens at once rather than having to share your whole display, but anyway, just asking for a moon on a stick, I suppose. Right, let's see what we want to do here. Let me copy and paste things to make this a little bit quicker. Copy and paste this bag. So again, if I try and print out B here, it's not going to tell me anything. I have to actually do some work on B for it to print out the value of B. And then I can do something more complicated than that. For instance, I could run an accumulate, which is a bit like a reduction. In fact, actually, if you've ever done an MPI, any obscure MPI, it's like a prefix scan in MPI. So accumulate will actually take the item on the left and add it onto the next item, and then add that onto the next item, and add that onto the next item, and so on and so forth. You can see it's taken 1 and added its left neighbor, and then it's taken 2 and added its left neighbor to make 3, and then it's taken 3 and added its left neighbor, which is now 3, and summed it up that kind of way. So those are the kind of operations we can do with Python bags. And of course, in this case, because all my data types are exactly the same, it's an expensive thing to do to have this as a bag, but I could have mixed my data types here a little bit. And then let's try, and it's quite happy to do these kind of mixed data types in parallel across my partitions. You can see it's by default I've partitioned it across 2 as well, so this is me specifying how many chunks I want to split this up across. Can I remember, there is a default I think for what the partitions is. I think the default might be 1. But I could be lying there. It could be that the default is to auto calculate there. So yes, I'm not sure there. So and then there's a question of what happens if I try now with this mixed kind of bag to do accumulate across it. Actually, I don't know what the answer is here. I don't know what this will actually end up doing. But there are other operations I can do where I can do things like try and select all the strings from this. Yeah, okay, so it doesn't like that. Addition because I've got mixed data types here, but I could do, and again I'm going completely off script here, but we still have operations we can do here, like something like count. I think now you can see here actually I've only got 5 data entries, and you can see yourself actually, I imagine, how slow this seems to be going. 5 data entries. Oh, I'm in Python. That was the wrong thing to do. 5 data entries, and I'm doing very simple operations on them. But there's a significant lag to kicking off that kind of functionality. And there you can see the overhead of doing the process stuff that Dask is doing for bags, as opposed to the threads stuff for that it does for data frames and other things. So again, if let me create this as a smaller data frame to see here, but if I do a data array, sorry, if I do a smaller Dask data array, which is like a NumPy array, it's still 1,000 by 1,000 elements. It's still pretty big compared to 5-element bag, and you can see that completes almost immediately. So there's 2 things going on here. One is that the bag is using the multiprocessor, which takes longer anyway, and the second one is that the data frame is going down to my underlying NumPy arrays, which are fast because they're done in C and they're parallelized, as opposed to the underlying Python code, which the Dask bag is going down to. Anyway, hopefully that gives you a little flavor of the different ways these kinds of things work. Actually, I also meant to show you, let me pull this into here. I've not put the pictures into these slides, which I should have done. But if I share this Chrome tab, you'll see that Dask, that's the picture I had into the slides here, but that seems, Dask can do some quite nice things as well in terms of what's going on here. So this is an example which I've run previously, and I've just saved in here of running a Dask data array of 10,000 by 10,000 into chunks of 1,000 by 1,000, and then I can use some functionality which probably doesn't work for you on Archer because you need to make sure you've got the right libraries installed, but you can get it to print out a Dask task graph. And we can see here, it's got a reasonable amount of different things going on here, with the stuff on the bottom level all being parallel, can be done at once, but then you have some other tasks which are not quite as parallel because they've got to wait for the data to be combined from other tasks, and likewise until we get all the way up to the top here. So, and that's one of the nice things about Dask, is that it has that kind of functionality. It has the data arrays, but it has the functionality to also do some quite nice sort of visualization things on it. And when we get up to actual parallel computing, you can actually do some keep track of your algorithms and your clusters, how they're running, those kind of things. Okay, but I won't spend too much long on that. So the bag can do other things. You can do reductions where you define a function that you want to run across the whole bag and then just run that. So you can see here we've got a isEven function we've defined, and then we create a bag from a list or from a sequence, and then we do this filter with this function, and it will pull out the data. And so we can do some more complex things than you'd think using user-defined functions to pull out your data in various fashions and push it into other places. You know, the caveats being, we've already mentioned that bags are immutable, so you can't change them, you can't update them when they've been created, but you can turn them into other things. And arrays and data frames are faster than bags, so it would be probably sensible to pull your data out and put it into another data form if you're going to then do some more processing of the data beyond that. Yeah, and if you're going to use bags in a big way, then have a look at the group by versus fold by function as well, because fold by can give you some performance improvements by doing reductions first and then grouping the data rather than grouping all the data and then reducing it down. And so there's some interesting optimizations that can be done there. Okay, as I also mentioned, you can do direct task graph computation using Dask, where effectively you take functions you've written yourself and then turn them into a graph that can run in parallel. So here's an example I've got, and as with a lot of this stuff in these slides is stolen directly from the Dask website, but there's a function to do increment a number, there's a function to double a number, and there's a function to add two numbers together. And then we have a loop over a list of numbers here, and we take each element of a list, we add it one to it, we double it, we add those two things together, and we create an output. Now you can see here that A and B can be computed independently, and that A, B, and C can be computed independently for each time we go around this list. So at some level we have 15 or 16, no, 20 independent operators, although the append may not be independent. And we have, even inside that, we have a bit of independence between the A and the B and the C. So it should produce quite a nice pattern task graph which you can run. And we can use the delay function. So one way we could do this is we could, you know, try and work this into arrays and make X and Y and Z be arrays and then do an increment. You know, NumPy lets us add one onto arrays. So we could do this with Dask arrays if these functions are pretty simple. If they're more complex and there's more stuff going on in here, then we may want to write that functionality ourselves, and we can do that using this Dask delay function. So that here, this here at the bottom, nothing in the functions changes at all, nothing in the data changes at all, but every time I call a function, I just wrap it with this function called dask.delayed, name of a function, arguments to a function, and each time we do that, that adds it into the task graph. And then that lets us create run the program. Now again, we've got to remember that Dask is lazy, so if we do all that, we have to call the compute at the time we've finished to make it actually do the work. Otherwise, it'll just produce a task graph and then finish. It won't actually compute it. And then there's actually another way of doing this using decorators, where you actually, okay, if you're calling inc and double and add lots of places in the code, I don't want to have to go through and turn them all into these dask.delayed inc and double and add. Actually, I can just put a decorator on the functions that I want to delay, and this will delay them everywhere that they're used. Now I still have to delay some things. So there's some function here I've not defined. It's coming from a library, so I need to delay that manually myself, and I still need to call compute, but that can be a cleaner way of doing this without changing all the source code as you're doing it. And then there's a slight thing to be careful of, actually, is if you get your syntax slightly wrong, then it will compile and, well, it'll run fine, it won't complain, but it doesn't actually do any delayed functions because it computes the functions immediately. So if you do your brackets wrong, so if you say delay then the whole function, including its arguments inside the brackets, then what this will do is just immediately calculate f, and then turn the output into something which can be used later by another, it adds the output to the task graph, but it doesn't, task going to be run. So that's not what we want to do. You have to be careful. You really need to make sure the brackets is around the function name, f in this case, which is not a very descriptive function name, but that could be sum or inc or double, and then the arguments of a function are outside in their own brackets, and then this enables Dask to pick it up and say, okay, I'm going to do this immediately. I'm not going to do this immediately. I'm going to calculate in the task graph and do it later. So this is the way that we can do more complex things in Dask, but of course this is a bit more work now. We're not now just loading up the data and just then using standard Python stuff. We're going to have to do a bit more work here in our code, but this lets us do more complicated things. As usual, if you have any questions as we're going on, please do shout at me. That's perfectly fine. And then there's a bit more of a functional thing called futures, which is newer, a bit newer, but it actually lets you do slightly more involved task graphs, which you can build as you're running. Because the delayed functionality is sort of build the whole task graph and then run it at the end, just like a lot of the other Dask stuff. Whereas futures is more designed to give you arbitrary task graphs, but also task graphs which you can self-generate and consume, and self-generate and consume. So it's similar to delayed, but you can get tasks to execute as soon as they're available, not build all the tasks and then run them at the end when someone calls compute. Now it still lets them go off and run and have dependencies and things like that, but it gives the scheduler and the functionality a bit more freedom. It's pretty straightforward to do. Effectively, you submit a function. You can also map a function, so you can also say take this function and run it on this set of inputs. So it doesn't have to be a single function submit, but you can say submit it on this range of data. And you can also create results. So you can say collect these results together and then move on. And there's functionality to let you move data backwards and forwards from scatter data out to workers before they work on it, or pull data back in from workers. Now you don't have to do this, you can just pull the future stuff together. But if, for instance, you've got some data sets where you know that a number of different functions are going to run using the same data sets, rather than getting Dask to work out those data movements for you, you can pre-scatter the data to the workers and then call the functions, and that can give you some optimized functionality. So what does that look like? Well, this is very similar to what we had before. We had our inc and our add functions. Now we're using a slightly different part of Dask, which is an extension to Dask called Dask distributed. And so we say from Dask.distribute import client. Now this is not installed by default on ARCHER2. You have to install this yourself using pip or conda, but it's pretty easy to do. And then you create a client, and by default it will start them as processors, or you can turn that out and start them as threads if you want. And then your functions as usual, and then you just submit the function. So you submit a function, you submit a function, you submit a function, and then you get the result at the end. And now you notice I don't have to do my compute now, because the submit starts the function off computing when I submit it, or when there's resources available to do it. So you don't have to call compute anymore. Likewise, I can also say actually submit this function here, inc, but to 1,000 different inputs, and then just collect all the results together here, and I can use them later. So that can let you build some more functional task graphs. As we've already alluded to, Dask generally defaults to thread parallelism unless you're using bags. or less using futures, which means it's sort of designed generally for single node stuff. It will generally try and use as many cores as are available, although you can restrict that. And that's not a terrible thing. That's lightweight work that will go off and do work pretty quickly for you in a lot of cases. It's easy to share data between workers, but it doesn't necessarily scale well up to large numbers of cores efficiently. So even inside a single node, you may not get the best performance running Dask with 128 threads across a whole node, compared to if you could run 8 lots of Dask, each with 16 threads distributed on the node doing different things, just because of what we talked about earlier today, where threaded parallelism quite often doesn't scale up to large numbers of threads very efficiently. It does better at small numbers of threads, particularly on the kind of architectures we have on the ARCHER2 system. So that means that if you've got the if you've got large amounts of work to do, but you can parallelize each bit, then we can start looking into these kind of hybrid parallelization schemes where I run a job array. It starts 8 jobs per node. Each one of those jobs has 16 threads. Each one of those jobs is doing Dask work using 16 threads on a node, and then I'm probably efficiently using all my cores and my nodes at the same time. Dask scheduling can, though, be modified by users, so that's the default. Actually, when we import Dask, we can say what we want it to do. So we can do dask.config. But we can also set the scheduler to be processed. So this is a global thing. We can say, specify for all the Dask stuff I'm doing, set up my scheduler to be processes instead of threads. If we want to, and this is basic Dask here. If we want to go a bit more complicated and use the Dask distributed, then we can use the client, and it has more things it can do. So we can do processes and threads there, but we can also then move on to things like using batch systems and submitting directly to the compute nodes and things like that in Dask. And this distributed client has this functionality to do a single node or multi-node. It has a nice dashboard as well, so you can see what your schedule looks like and how your threads are going, your workers are going. And so what does that look like? So you can specify for normal Dask the schedulers on a per compute option. So you can say for each compute, you want to specify what scheduler you want to use. You can do it in a Python context where you say, okay, for this bit of code that I'm going to run, I want to configure with threads here, anything that's inside this scope here. So that's multiple functions you can have as long as they're indented at the same level as this width. Or you can set it globally, as we've seen before, for the whole program, configure my scheduler like this. And again, it depends what you're doing, but most of the time, if you're just doing single node stuff, you might be fine just having the default scheduler as threads. You can also programmatically inside your Python script set how many workers you want. So you can either specify a particular kind of thread pool like this at the beginning of the program, say my thread pool is 8 and I want 8 workers, or you could do that with a context like this. Or if you're using the distributed scheduler, you can specify it when you create it, the number of workers you want. So you can control how many workers you want in Python. The distributed scheduler has much more functionality in it. So you can do normal compute stuff, but we can also integrate with a number of different schedulers, batch schedulers. So it lets us integrate with a Slurm system that ARCHER2 has. But if you're running elsewhere, you could integrate with PBS or SGE or a Conda cluster, all these kind of things. And so that's possible. That actually is in another separate Dask library called Dask_job_queue. And so you have to install that as well. But once you've installed that, you can submit jobs from the login nodes directly to the compute nodes using the scheduler system. It will let you do that. And there's a final module you can use, which is something called Dask_MPI, which is another thing you'd have to install. But that lets you run your Dask program using srun or an MPI job launcher to take your program and start it up for you. So you could just use Slurm to give you 8 nodes, and then you could use srun to start up, 8 times 128 workers and submit it that way. And there's various different things you can do for that. Actually, on ARCHER2, this is what it looks like. It looks a little bit complicated, but if you wanted to submit to the compute nodes using this job queue thing, you actually define a Slurm cluster. You put in all the things that we see here from the standard batch script we've seen before, like your project and what you want to do. You have to add in a little bit more, so your Python user base, so it picks up your modules correctly and your installs correctly. But once you've done that, you can then say, for this cluster, I want to run on 2 nodes, create a client, and then when I do this work down here, x.mean.compute, instead of doing that on the login node, what that'll go off and do is it will fire up 2 single node jobs on the Archer backend, and then it will send my data off to them, do the work, and pull the data back. Now, of course, if you've got some quite heavy work to do in your Dask thing, then you're probably best not doing it from a login node. And what you want to do is put this inside a batch script, submit this to a compute node, and then it will itself generate new jobs that run on other compute nodes. And that's perfectly acceptable thing to do. As we've already seen, we just have to follow this standard Python approach to installing Dask distributed in job queue. The normal Dask is already there for you. And because normal Dask is already installed for you, then you can just run it as normal. So just Python Dask program, stick it on a compute node, and away it goes. Or you can, as we've seen before, do interactive job submissions of your Dask programs. There's lots more to learn about Dask. There's nice integration to Jupyter notebooks and these kind of things. And there's the dashboard, and there's lots more functions that I've not shown you for each of the things: Dask, the array, the data frame, all these kind of things. But that's probably a reasonable introduction to get you started. And then it's a question of you playing with it and having a work out to see if it works for your application or for your data set or for what you're wanting to do. But there are a couple of sort of guiding principles for Dask. The first one might seem a little bit strange, but it's, if you don't need Dask, then don't use Dask. In the sense that if all your data will fit inside a single node, and you're not particularly restricted by runtime, then using NumPy arrays directly or Panda data frames directly is always going to be faster than doing it through Dask, because Dask has a bit of overhead with the task scheduler and configuring things. Actually, when you come to use it, you'll see that when you first start up Dask, it can take a bit of time. So if you've got things that fit in memory and you're not taking minutes to compute each thing, then you're as well not going to Dask yet. But if you do need Dask, if you need to parallelize because you don't fit in memory or you want to use more compute resources, then it's definitely a good place to start looking at. Depending on what you're doing, you have to be a bit careful about how you split up your work or your data across workers. So because you specify the granularity in various things, you have some control over how. So if you take a very large array and make the chunk sizes far too small, then your performance will be terrible because it's going to spend all its time fetching and sending chunks around. Likewise, if you make your chunks too big and don't expose enough parallelism, then there's a chance that you also run into problems because yes, you don't have many overheads, but you're not going to get much performance improvement because you're not letting the use as many workers as it could do. So there's a little bit of manual tuning sometimes to do there to make sure you get good performance. One of the guiding principles of Dask is you definitely need to call compute unless you're doing features, but you definitely need to call compute and everything else. But don't do it too often. Ideally, if you can do it right at the end of a program once, then that's fine. That gives Dask as much scope to schedule tasks efficiently and reuse data between different tasks and all these kind of nice optimizations. Now, of course, there may be times where your task graph gets too big, or you just, you need results from one iteration of something before you can move on to the next iteration of something where you have to call an intermediate compute step. But if you can avoid it, then avoid it. As we've said a couple of times, if you're starting to move up to large numbers of processors, large amounts of workers, then this idea of mixing threads and processors might be sensible. So having using the Dask Slurm scheduler to start up workers and distribute those across nodes, but inside each one of those workers to do something with threads from a normal Dask schedule might give you better performance than using all workers across the nodes with no threads. If you're going to load in data, then if there's a function that does it natively in Dask rather than loading it into NumPy first or data frame first and then copying it across, it's probably best to use that, because that will at least give you the in-memory blocking functionality which let you load larger data sets, and it avoids having to copy data between different libraries. And we haven't gone into much detail here, but persisting data to memory when reduced can help as well. So actually, if you're going to do some data operations where you group by and reduce the data sets into a much smaller data set, then taking that and persisting it into a single smaller data set which is not blocked and out of memory, then that can give you some performance benefits there. But I should really put a summary slide here. The summary slide here is Dask in general is pretty easy to use, and take an existing parallel program and turn it into something that runs in parallel. It's an existing Python program and turn it into something that runs in parallel, with the caveats that, of course, there are challenges to doing that, and you can get it wrong and produce something which doesn't run as fast as it could do. But it's pretty easy to use, and it's reasonably well integrated with ARCHER2. So if you're interested in using ARCHER2 and Dask, then where did I drop out? Had I given my summary? Yes, 1 minute. So had I finished saying that Dask should be easy to use in ARCHER2? If it's not, let us know. Yeah, I mean, apologies if the audio dropped out there. I don't think you'll have missed anything hugely important. All I was saying that we should be reasonably integrated with Dask on ARCHER2. There may be some things, if you want to use it in anger, you need to install, like distributed and job queue, and you may need to play around a little bit to get it doing exactly what you want it to do. But it is generally straightforward and quite intuitive to use. So give it a shot, and if it's not working, then let us know, because there may be something we need to fix there. Okay, if there's, other than me dropping out, if there's no other questions, what we can do is you can keep going on the things that you've been doing really well at, including the I/O stuff, which is definitely interesting. There's a practical 4 here. Practical 3 should be in there as well. I'll check the repository why it's not there. Practical 4 here is a Dask practical, which there's a couple of little things to play around with, just getting started with Dask on Python, on ARCHER2 using Python. But then there's some little functions to actually try and parallelize yourself. One which is the one we've seen in the slides, so shouldn't be too difficult. And then one which we've not seen in the slides, which is something which calculates the Mandelbrot set, and you should be able to parallelize with Dask data array. Both of these I've put solutions also in the directory, in the Dask directory, in the exercises. So if you really are struggling and you don't want to ask for help, then you can have a look at what the solutions are. So give that a shot for the next 20 minutes, and then we'll come back and we'll give a final lecture on R between 5 and half 5. And I'm sorry to wrap up. Apologies, we are overrunning slightly, but sorry about that. But see how you get on and let me know. And if you need to head off, that's fine. The next set will be recorded and the lectures will be up. So if you need to drop back in and replay the recording to see what was going on, that's perfectly fine as well. And I'll fix this practicals so the third one's up as well. Yeah, Ed, if you have a question, you can send me it or just shout out.
Hello. Yeah, I'm keen to do this Dask practical, but I'm still on practical 1, and I just wanted, I mean, I think I've pretty much got to the end, but I just wanted to check with you what the sort of answer, what the answer was. Basically, I think I've understood that if you put lots of threads, then there's increasingly an overhead associated with that. So based on the kind of the timings that I was getting out in the out files, it seemed to be that like 128 processes and just 1 threads was fastest. Is that expected?
So it sort of so is this the streams benchmarking?
Yeah, that's right.
Yeah. So sort of, yes. Actually, on streams, it's an interesting one. You can probably get slightly better performance if you underpopulate completely and actually just have something like 16 processes and no threads. And as long as the 16 processes are spread across the node efficiently. So there's a kind of graph of memory bandwidth where you need enough workers to get the full memory bandwidth, but when you add too many workers, there has to be a bit of contention. You start to lose that kind of stuff. But what you've seen is absolutely right. You can use 128 workers and still get good performance. So what I hoped would come across is that you can use 128 workers and still get good performance. You can also split it up and use some workers and threads, and it may have a little bit of performance impact, but it shouldn't have terrible performance impact. But the thing we do also want to avoid is if we get the binding wrong, which it sounds like you've not done, which is good. If you get the binding completely wrong, then you can get very bad performance because all the threads end up on a single processor, a single core, or you don't spread out across all the cores properly, and then suddenly you get a fraction of that. So I'll see if I can come up with an example where that happens. But I think if you've got sensible performance numbers and the 1 to 8 MPI processes together looks sensible, then that's fine. The thing you could do is try completely underpopulating and doing something like let me see, let me put into the chat. So if you said something like tasks per node equals 16 CPUs per task equals 8, but also threads equals 1, so then you don't spawn those extra workers, then it'd be interesting to see if that gave you a even better performance than you were seeing before.
Oh, okay. Is it so? Is it right that so basically whatever happens, the tasks per nodes multiplied by CPUs per task should be 128.
Correct. Yeah, that's what we would hope. That's what we're generally looking for, unless we go a little bit more advanced and try and do some of this hyper threading.
Yeah.
Yes, in general, 128 is the maximum workers we've got, and we can use less than that if it makes sense. But the sort of default is 128.
And then where does the threads? Just a bit unclear about how. So that I think I grasp, but how the sort of threads variable, how that sort of corresponds to those numbers.
So the threads variable is specifying the number of workers per process. So it's a little bit involved, but what we do is we start a bunch of processes running, and then each one of those processes can create its own workers, and those are threads. And so what in this example doing, the threads variable is specifying an environment variable called OMP num threads. And this is something the program itself is picking up and saying, oh, you want me to create 8 workers, I'll create 8 workers. And each one of those processes does that. And that's how they can create their own mini workers to help them with their task. Now, you don't have to do that in a program. As you've seen, you can run 128 processes and use the whole node and still get good performance. But there can become times where you want to underpopulate because you want more memory per worker. And so you create, say, 16 MPI processors and give them each, but then you've left over some spare cores. You've left over, you've out of your 128 cores, you've only used 16. So you can say, oh, actually, let's give each one of those MPI workers a process, each one of those processes 8 threads, and that uses all my cores still, and they can use their workers for whatever they want to do.
Right.
That makes sense?
Yeah, I think so. I think so. I think maybe it would be. Is it possible to send me some like documentation to go away and read about how to sort of do this configuration well? I think that would be really helpful.
Yes, definitely. Can you email me directly and I'll reply to you?
Yeah, sure. I'll do that. Thank you.
That'll be useful. Thanks. My connection's a bit poor, so I'm going to drop out and come back in again. I hope that fixes that. I'll be back in a second. Sorry about that. This Collaborate session decided that I couldn't get back in for a reason, for a while, so there we go. But I'm back again. I'll just do this final wrap-up lecture on R, which is a bit shorter than the rest anyway. And then we can call it a day, and I'll put in the practice examples of R into the repository, which you can try out in your own time as well. So this is sort of a similar kind of thing to the Dask one, a little bit less involved actually, because there's lots of different options in R, and so this is just to give you a bit of a flavour of what's possible in terms of parallelizing things using R in general and on ARCHER2, but we're not going into the same level of detail as we did in Dask. If people are more interested in this R stuff and want some follow-up data and some more detail of specifics, that's fine. Just let me know, and also let us know in the feedback form for the session today, and that will be useful things to know. But we'll see how this goes. Well, that went very quickly. Give me a second, and I'll start that again. This happened to me last time, when I was teaching last week as well, a couple of times, where Collaborate wants to rush through the slides. So let me try that again. There we go. That's better. I'm hoping you can all hear okay. Apparently I've got low quality connection again, but so let me know if I drop out, please, and I'll try switching networks. Thank you. Okay, so as we've seen for other things we've talked about today, then we have different kinds of requirements for parallelizing R, just like we do for Python or anything else we've got to undertake. You know, too much, you could easily break it down for R into 3 different things. Oh, I'll put the parallel slides up in a second. Sorry, I'd forgotten I'd not put them in the repository. They will go in as soon as I finish speaking. Apologies for that. There's a couple of different, in fact, let me put them in now whilst I'm speaking. Let's do a bit of multitasking. There's 3 different reasons you could break this down. Now, of course, you could do different breakdowns for requirements on parallelism for all the kinds of languages and programming exercises you're doing, but particularly for R, it sort of seems to make sense that you could have these different requirements, but you come into parallelization, and I think it's probably actually true as well for very much so for Python, in that it could be that you have particular requirements for computation, so my program takes too long. And so that we're sort of talking about individual computations are taking a long time, let alone trying to run on large number of data sets. And because they're taking a long time, you want to add more resources. It could be that you've got too much data to process. And so that doesn't necessarily have to be, you know, one big file. It could be lots and lots of little files. But you just got loads of them to process, and that is absolutely as I've said before, what ARCHER2 is generally designed for is sort of these large-scale, parallel, tightly coupled jobs. But we also see use cases where people just have very large amounts of data to process through in a feasible time, which you couldn't do on other kinds of resources. And then, of course, my data is too big. So I may not have lots of files to process, but my individual files themselves are too big to process. So I need to do something about that. And that's, you know, that motivation is something we've seen as well for Dask. So Dask provides this in-memory compute option where you can load up and process files that are larger than you can fit in your memory. And there are other things in Python that let you do that, X arrays and stuff like that, packages like that. That allow you to do that, and the same is true for R. Okay, so we can see those different things, and then so just like in Python, R has lots of different. You know, it's got a large universe of libraries and functions that people provide. So there's actually quite a lot of choice out here for different things where you can add parallelism to R or exploit parallelism through R using. So if you go and have a look at the CRAN R project website for high performance computing, which is updated very recently, you can have a look and see the different things that are available. And that's from, there is a bunch of functionality now, and it didn't used to be, but it's now built into R. And it's been for a few years. But if you went back 10 years, for instance, a lot of this stuff you'd have to bolt onto the side of R to give you a parallelization, but now it's been there. And so there's implicit and explicit parallelism, with implicit parallelism being the kind we've seen with NumPy in Python, where that library itself is calling some other libraries underneath which give you faster performance, faster runtime, because they're calling down to functions which themselves use something that's parallel. And then there's explicit parallelism, which we'll look a bit at today ourselves. And these include packages like Snow, which we'll come on to look at, and RMPI, and some of the threading packages which are there. And then there's a bunch of what you call applications, which are large-scale Python libraries, which themselves are calling MPI underneath, or calling some kind of parallelism underneath. And then there are a set of packages which gives us batch system integration, hardware resource integration, including a lot of GPU packages, and distributed computing integration, so into things like Hadoop and Grid. If you go back, if you're as old as me, you can remember grid computing. Those kind of things are around. And finally, we have packages that let you do big memory in memory computing and native code interfaces. So if I was doing a 2 or 3 day course on R, then I would teach, part of what I teach is how you interface to other codes like C and Fortran. So if you need to, you can compile down and get parallelism or improve performance that way. But it's definitely worth having a look at this website here. It gives you lots of different options for using, for parallelizing, or giving you parallel functionality using R. If we look at picking some of those out ourselves, now there's lots more here. So again, this is not meant to be exhaustive lists and not meant to be particularly choosing one or the other and saying it's better, but ones that I've seen or used or I'm aware of. And you can have a look at functionality at different levels. So trivial parallelism, we could call it, or sometimes called embarrassingly parallel functionality, where actually you've got a function where you've got no real communication between the tasks for independent tasks. They're just like what we saw in Dask, independent tasks, and we can just go off and do them independently. So we can see things like map and lapply or various versions of that, which can be turned into things that can run in parallel. There's for each loop parallelism and threads through a package called RDMS, RDSM, should I say, sorry, RDSM. And then there's and again, this is not meant to be exhaustive. This is just to give you a signpost. These kind of things are out there. And then there is distributed memory parallelism, which actually lets you run multiple processes inside a node and go beyond that and see run across multiple nodes. So parallel and the stuff that's built into there will do in single node stuff, and then Snow and RMPI and some of the other functionality. PBDR will let you go across multiple nodes and run your R workflows or your R functions in parallel across there. And you can see here that, you can imagine that RMPI here is very similar to MPI for Pi in Python and MPI library in C and Fortran, as it gives you explicit control over how to do these kind of writing the parallelism yourself. But then we have higher level functionality like Snow, which tries to do some of that for you, similar in some ways to how Dask is doing tasking, but not quite the same. But it gives you functionality on top of that to try and improve the performance with but but by not requiring you to do all the work yourselves. And so we can have a look at the sort of automatic level parallelism, which I think we would call down here implicit parallelism, in that R itself has a reasonable amount of parallelism built into things already. So there's an example here that BLAS libraries and other underlying functionality use shared memory parallelism already, or they can do if you've built your R in such a way that it uses things like the Cray libsci, which we have on ARCHER2. So, you know, one of the good reasons for using the pre-compiled and pre-installed R for you is that it's already there. So let me see if I can do this sensibly with matrix. Yeah, okay. So let me just try and do another live demo. I'll just share the screen. So here we've got I've created a function here, a script, which has creates a matrix, two matrices of a particular size, and then it runs a multiplication a times b at some location. Now I'm doing it multiple times here just because this tends to be quite quick, and what I want to be able to try and show you is the operation of that when it's running. But if I just do a single one, it runs too quickly and I can't see what it's doing. So let's just see where we're at. So we've got R is working properly. I've got things installed. So this won't produce any output, but should run, and it's running reasonably slowly, which is good. It should be able to let me be able to show what I want to see. Actually, it's maybe running too slowly for me to want to show what I want to see there. But let's see. So if I do this, no, I want to do this instead. Just get myself ready. So I want to see actually what process I've got running, and the nice thing is this is a little thing that I can track what I'm doing on the login nodes. And the nice thing about it is it tells me how much CPU time things are using. So 100% here will mean I was using a single core completely. And beyond that, if it goes above 100% here, it means I'm doing stuff in parallel. So let me run this R script in the background. So whilst it's running, I can also look what's going on. And we can see here, this is the R script here. And look, already what we can see is R is running at 8,000%, 10,000% of the runtime, and now it's finished. So what that can tell me there is actually those things that I'm running in the R. And the interesting thing is actually, if you look at the matrix.R script, actually it spent a while not doing anything in parallel, and then suddenly it went in parallel. And what that's telling me here, or what I know here, is that these matrix creation things aren't parallelized. They're done in serial. But this matrix multiplication is parallelized automatically for me, and you can see it's going up quite quickly. Actually, the way it's configured on ARCHER2, I can control how much parallelism is used there. If I use this OMP nubthreads environment variable again, and then do exactly the same thing I did before, what we'll actually hopefully be able to see here is this CPU performance tops out at 200%. So actually I've said, actually, I don't want you to use more than 2 cores for this. Please restrict yourself down to that 2 cores. So it's an implicit parallelism, but I do have some control over it. I do have the ability to go in there and restrain that, but I'm not choosing what's parallelized. I'm effectively saying, you parallelize what you want to parallelize, or what you've been built to parallelize with, and anything else, I'm not getting any performance benefit with that. But yeah, so that's showing us that R can do some parallelization stuff for us automatically, and just like Dask, if you let it, it will use all the calls that are available, and that may not be, or that may or may not be a good thing for you. But you can control that on ARCHER2 using this OMP num threads because of the way we've set it up or configured R. Let me just stop sharing that. Go back to my slides. I'm going to guess this is going to share slightly the wrong thing. It has shared slightly the wrong thing. Apologies. Let me just fix that. I think it's got to the end of the day for collaborating. It's just decided it's not happy. Okay, there we go. So this should come back through. So yes, and there's some other functionality that will automatically give you these kind of things here. So for instance, the library data.table, now this is not installed by default for you on ARCHER2. You'd have to install that as a package. But if you install it and import it inside VR terminal, you'll see when it comes in, it says by default data table 1.14.2 using 128 threads. And I can actually control that if, again, command line I export OMP num threads is 2, then I can specify in there that I only want 2 threads and it will come in using that. So there's some built-in functionality where I can get automatic parallelization and get performance there. But I'm not controlling exactly what kind of parallelization I'm getting there. I can just control what kind of workers I have. Now, beyond that, we can do what I'm now calling trivial parallelism, in the sense that this is automatic parallelism, trivial parallelism, which you could call embarrassingly parallel applications, are ones like we've seen before, where you just want to run lots of independent versions of the same code, possibly varying by a different input parameter, and that could be a Slurm job array with that data coming in. And so in reality, there's nothing I need to do to support that, except read the command line arguments in, and then take those command line arguments and do something with it, and then just run my code as normal. And then I could just do, you know, R script inside my batch script, R script, the name of my R script, pass in whatever data I want to pass in to differentiate between the different runs. And this could be a Slurm job array number like we saw before, and that will trivially run this on as many workers as I want, because I just set up my batch script to do that. Of course, it's not particularly functional parallelism because I'm not doing any processing of the results together. I'm not doing any reductions of data or anything like that. I'm just doing all the work, saving all the data out, and at the end I'm then going to have to go through and process all that data. So it's going to give me some work at the end, but again, it's something we could do to do this parallelization. And it does also require some care if you're going to be using R to do things that use random numbers. So we've got to make sure that we are either using a parallel random number generator or seeding the random number generator in such a way that we're getting genuinely random numbers between our different runs, if that's what we need for statistical independence, or genuinely the same set of random numbers if that's what we need for our program as well. And this is what we're doing in this example here. You're taking in an argument and you're using to set that as the seed for the random number generator. You can also then move on from trivial to just trivial parallelism. And these names are a little bit flippant. They're not really trivial, but they're not communicating parallelism. They're not really tightly coupled parallelism. And really, at this level, and there's nothing unique about R here, but this is how the workflows break down. You could say the same about the stuff we were doing with Dask and parallelism there. What we have to do is we have to sort of do this idea of split the data, apply some function, and then combine the data again. And so what we're seeing that's different from the last slide here is that we now have the idea of doing some work inside there on the data splitting and the data combinations. So you're going to want to partition the data into groups to be worked on, apply the operations to each group, and then combine the results with some form of reduction at the end. Now, the interesting thing about this approach, and again, it's nothing that's specific to R here, but the same is true for Python or any other program that we may want to parallelize like that, is that quite often you have to make your program more complicated before you can parallelize it. And so this is an example actually I borrowed from a collaborator, Glenn Lockwood, from one of the US labs. But you know, this top bit of code here, you read in a data set, you call a k-means function from R on that data set, you print out the results. And that's pretty simple. Now, you're not getting any parallelism there. But one of the key ways to do parallelism in R, just like we saw in the Python Dask stuff, is to encapsulate something into a function and then call that function on different data sets. And so a simple way to do that encapsulation here would be, okay, we're going to take this call here, this k-means call here. We're going to turn it into a function, read a data and turn it into a function, and then we're going to apply that function to different inputs. And then we're going to collect the data from that function at the end into our final result. Okay, and so that one there is going to be, it's more function, there's more work to be done here, but then when we've got to this point, we've actually going to have four different function calls that potentially we could run in parallel. Okay, now actually this code here isn't doing anything parallel. It's just split the data up and turned it into functions that can be run. But it's the preparatory work that we need to do to make it possible to run in parallel. So if we have a look, then once we've done that work, it's then possible to use some functions from the inbuilt parallel library from R to then to make sure that that actually runs in parallel. And that's pretty simple. So actually we can use this MC apply, which is called MC apply because it's multi-core apply. It doesn't really mean multi-core, it sort of means multi-thread apply, but we can do MC apply, and now this should run in parallel. So we've imported a new library, we've applied this function MC apply, and everything else you see sits the same. So it goes off and does the work on these four functions and brings back the results at the end. We could also do something quite similar with another function called MC parallel. So there we're not doing, we're not just applying a function to a data space, but we're doing bespoke parallel functions. So again, this is MC multi-core parallel, and we have defined a, what we pass in here is up to us. Here we're just passing in a data range, but we could pass in functions to this MC parallel and it would produce results at the back end. And then we can collect those results once the parallel computation is finished and get a result out of that. So there's an example down the bottom here of reading a data set in and then using MC parallel to do different things on that data set and then collecting the results at the end. So you can see that the MC apply functions, we're applying the same function to the different data, whereas MC parallel is a bit more functional in the sense that it allows us to do different tasks on the same data at the same time. But then, of course, we have to manually program out what we actually wanted to do, whereas in MC apply, then we don't have to do that. We just have to give it a range of things to run across. And then likewise, there's a different library which does similar kind of things, but not the same. It's worth mentioning, which is the for each library. And so this, a bit like the MC stuff, multi-core stuff, is a way of converting a function call or an apply call in that case into something which is iterated over various times. So you can see here there's a for each function which looks very similar to what we were doing here with these applies. For each, do, and then the function inside here. So again, we've now not got separate functions. We've just got code blocks with what we want to get done inside them. We don't have to create those separate functions. But we can do this for each. We can generate the results and pull it back again. Now again, this isn't doing anything parallel yet. But if you convert it into a for each, and then you do a do par using these libraries up here, and you set up for workers, for threads, then this is doing the same thing we're doing on the MC apply, lapply we saw down here. So that's another way we can do. And so again, remember these are still in node parallelizations for our functions, but we can take that to another level. So we can actually then use this library called Snow, which is I think something network of workstations is it stands for. I can't remember what the S stands for. Synchronous network of workstations. Anyway, it's designed to connect together multiple nodes and run in parallel like we do in our MPI functionality. So you can take similar kinds of approaches, and instead of doing MC lapply, we actually use the Snow library and use par lapply. And this does exactly the same thing, but because we've configured it here to use an MPI cluster, then we can run it across multiple nodes as long as we launch it in the correct way. So this is a sort of simple example of how we can take that forward. But again, it's still dependent as construction functions that we can map across these kind of areas. And exactly the same as for the apply functions, we can also do for each and do exactly the same thing. So now we've registered a Snow handler, and we're going to do a do par across that, and that does exactly the same functionality. We're nearly done, people. Thanks everybody for hanging on to the end. I'm sorry we've gone on for so long. We are nearly done. So again, once we've done this transformation of the code into something which can run multiple times, then we're able to run different kinds of use different kinds of libraries to run across different kinds of infrastructures. Now, at a more generic level, we can use this Snow cluster directly to create functions that we can run across as many clusters as we want, or as many processes as we want. So the generic Snow functionality uses this. We set up an MPI cluster, we create a function, we run that function on the cluster, and then we get the results out at the end, and this will produce the results. And so if we take a very simple Snow function like that, we can run it using something like srun, and Snow can give you a function, a handler called rmpi Snow, which will take that and run it for us. Now you can see my batch script now is something slightly different than we've seen before, because I need to make sure I set up R in the correct way. I've loaded R, I bring in my lib path, I set up my path for my install, and then I submit my application as that goes on. That's of course very simple functions. You can actually go more complex and do, proper functions where you're going to go through and calculate. In this example here, you're going to calculate the probability of people having a birthday on the same day if you've got a certain size set. So this one here, we're going to have 100,000 people, and we're going to try and calculate what's the probability of 2 people in that set having the same birthday. And we set this up now as something that's going to run inside our Slurm batch script. So we work out how many workers we have directly from the Slurm environment here, using this call at the top here. We create an MPI cluster, and then we use the number of workers and other functionality here to configure what we're going to do with our function. And then we can run our function using this cluster apply approach down here. I think I've actually missed out the bit of code where we apply n workers to the MPI cluster. I think we apply it direct to the MPI cluster here. I'll fix those in the slides and repush them. And then you can just run that function, and that will take your data or your function and run it across all your workers, pull the data back, and then you can process it locally and produce our data that way. And again, we can run that with this RMPI Snow function to take that and run that on Archer, quite easily run that on multiple nodes across the system and scale it up that way. So there were just some simple examples, I appreciate we're out of time now, of how we can take MPI, take our examples and parallelize them either on a single node or across nodes, to give you access to all the hardware we have available on ARCHER2. There is functionality there below that to write much more complicated programs using the RMPI library and things like that. But for most people, you probably won't do that. You can probably find a combination of what you need between array jobs, between local node parallelizations, and sending things off to more complex things using something like Snow. I see there's a question in the chat here. So do Snow is a extension of the Snow package, which adds in that do par for each. So it's a sort of bolt on the side of both for each and Snow to let you use for each inside of Snow. So it's a sort of an extension. It needs both Snow and for each to work because it's designed to adapt between the two. Okay, so I know we've gone through a lot of detail there, and you've not had as much time as I would have liked to actually try out some of these exercises on the system. Apologies for that. I obviously need to tweak the timing slightly on the lectures and take about a bit of material out. But I hope you've got a little bit of a flavour through the day for what ARCHER2 is and how we can parallelize things like Python and R on ARCHER2. And hopefully then if you have data science workflows, that gives you some scope to say, okay, I can see where my workflow would sit into this. If you think, well, actually I've got a workflow and none of this is appropriate, then I'd be very keen to hear from you, because I think it'd be quite nice to understand some of the workflows that don't fit into these models we were thinking about here. And so we will, as well as the feedback you can provide, you can get in touch directly and say that to me. Yep, there are exercises for R. I've not pushed them up yet, but I'll do that after we've finished speaking. So there'll be some chances to try out VR exercises and play with R yourself. And as I say, give the exercises a try if you have some time and available energy over the next few weeks. Even the ones you've not tried. If anything comes up and occurs to you, or it doesn't work, or you don't understand what's going on, then do feel free to get in touch with me directly whilst you're doing that. And it would be interesting to know what your feedback is from the exercises of the lectures if you have any. So are there any questions? If not, then I will finish there. I'll stop the recording. I will get the R exercises and I'll correct the lecture and put that up as well. And I'll like to thank you for coming along. Hope it was useful. And as I say, we'll have a feedback survey going out shortly to you, and it would be useful to know, particularly those things like what was missed from the course, or what worked well for the course, or what you'd like to hear more about, and that would help let us redo this and improve it for the future. Otherwise, thanks for coming along and hope you have a good day.